Hi everyone, I am Rishi Panchal. Imagine a world where a single country controls the brains inside every phone, car, and supercomputer on the planet. What if China, already the world's manufacturing powerhouse, could produce all the advanced semiconductors it needs completely on its own? How close is that vision to becoming reality? And more importantly, what would it mean for the rest of the world? Today, we're diving deep into one of the most critical technology races of our time. We'll explore exactly how far behind China really is in the semiconductor industry, what's holding them back, and whether they can actually catch up to the leaders like Taiwan, South Korea, and the United States. By the end of this video, you'll understand why this isn't just about technology. It's about economic power, national security, and the future of global innovation. The grand ambition. Let's start with China's bold vision. Back in 2015, Beijing launched its Made in China 2025 plan with an incredibly ambitious target to produce 70% of all the semiconductors it consumes by 2025. To put this in perspective, achieving this goal would have required nearly every new chip factory built worldwide over an entire decade to be located in China. It was a moonshot goal that many experts considered almost impossible. Well, 2025 is here, and China is still importing hundreds of billions of dollars worth of chips every year. So, what happened? Where did this ambitious plan fall short? The answer lies in understanding just how complex and challenging semiconductor manufacturing really is. This isn't like building cars or smartphones. We're talking about some of the most sophisticated technology humans have ever created. Think about it this way: modern computer chips contain transistors that are smaller than viruses. We're literally manipulating matter at the atomic level to create these electronic brains. And China discovered that catching up in this field would be far more difficult than they initially imagined. But here's what's fascinating: despite falling short of their 70% goal, China hasn't given up. In fact, they've doubled down on their efforts, and the progress they have made is actually quite remarkable, even if it's not headline grabbing. The lithography bottleneck. To understand China's biggest challenge, imagine trying to create an intricate, detailed painting using only a thick, blunt brush, while your competitors have access to the finest, most precise brushes available. This is essentially China's situation with lithography, the process of etching tiny patterns onto silicon wafers to create computer chips. The most advanced chips today require something called EUV lithography machines, extreme ultraviolet machines that can etch features with nanometer precision. These machines are absolute marvels of engineering, and there's only one company in the world that makes them: ASML, a Dutch company. Here's the problem: China has exactly zero EUV machines. Due to pressure from the United States, ASML is not allowed to sell these cutting edge machines to Chinese companies. So, what does China do? They get creative. Chinese engineers have developed workarounds using older DUV technology, deep ultraviolet machines. They use a technique called multiple patterning, where they expose a chip multiple times with DUV to achieve what one pass of EUV could do. SEMIC, China's leading foundry, actually managed to produce a 7 nanometer chip using this technique. That's genuinely impressive engineering, but it's like creating a complex design by carefully overlaying several stencils. It's possible, but it's much more difficult, time consuming, and error prone. Intel tried a similar approach when they attempted quad patterning at 10 nanometers, and they ran into serious problems with low yields and delays. Now, Chinese companies are pushing this even further, aiming for 5 nanometer class chips with quadruple patterning. Meanwhile, companies like TSMC and Samsung are printing 3 nanometer chips using EUV as standard practice. It's like China is running a Formula One race with a modified streetcar. Impressive engineering, but they're still at a fundamental disadvantage. The generation gap. So, exactly how many generations behind is China? Let's break down the numbers. Today's industry leaders, TSMC, Samsung, and Intel, are manufacturing chips using 3 nanometer processes with 2 nanometer technology on the horizon. In contrast, China's most advanced manufacturer, SEMIC, only achieved 7 nanometer production in 2021, and even that was in very limited quantities. When industry analysts examined SEMIC's 7 nanometer chip, they were genuinely impressed. It was truly 7 millimeters and represented a remarkable achievement given the restrictions on Western technology. However, they also noted that SMIC's approach used less aggressive scaling, making it more comparable to an early 7 nanometer process. But here's the really telling statistic: Nearly 95% of Chinese owned fabrication capacity is still using 28 nanometer technology or older. That means only a tiny fraction of China's chip manufacturing can even attempt what TSMC and Samsung were doing 5 to 7 years ago. This isn't necessarily a problem for everything, though. Most Chinese foundries focus on mature nodes, 28 nanometer, 40 nanometer, 65 nanometer, which are perfect for things like microcontrollers, power management chips, and automotive electronics. Chinese companies actually excel in these areas, and these older chips are still absolutely critical for cars, appliances, and countless other devices. But here's the business reality: the truly advanced segment, chips below 7 nanometers plus specialized processes, accounts for about 70% of the semiconductor market's value. The mature process segment, where most Chinese firms operate, represents only about 30% of the market value. So, while China is building impressive manufacturing capacity, they're largely absent from the most lucrative part of the market: equipment and materials. Challenge chips aren't made with just dreams and brilliant engineers. They require an army of ultra precise manufacturing tools and specialty materials. And this is where China faces one of its biggest bottlenecks. Despite years of massive investment, China still imports the majority of its semiconductor manufacturing equipment. Between 2017 and 2022, China imported $93 billion worth of fabrication tools, more than any other region in the world during that period. But here's the crucial detail: not a single one of those imported tools was the latest and greatest equipment needed for cutting edge chip manufacturing. Thanks to US export controls, Chinese companies can't buy the top tier equipment needed for sub 14 nanometer manufacturing. This has effectively frozen China out of the high end equipment market. No EUV machines from ASML, no advanced scanners from Nikon, no state of the art photoresists from Japan. What's left are older generation tools, which China has been stockpiling aggressively. But China isn't just sitting back and accepting the situation. They're pushing hard to develop their own equipment industry. Companies like Nora and AMEC are making significant progress in areas like etching and deposition tools. Since the US restrictions began, these Chinese equipment makers have seen explosive growth. AMEC forecasted over 40-50% revenue growth in 2023 as local fabs desperately sought alternatives to Western suppliers. However, let's be realistic. While these companies are making genuine progress, they're still years behind industry leaders like Applied Materials and Lam Research in terms of technology sophistication. China's approach to materials is particularly interesting. They're one of the world's largest suppliers of rare earth elements, which are crucial for many high tech applications. In a classic case of economic retaliation, after facing chip sanctions, Beijing imposed export controls on gallium and germanium in 2023, followed by antimony in late 2024 and indium in early 2025. These materials are vital for certain semiconductor substrates and high speed chips. China is essentially saying, if you won't sell us your advanced equipment, we won't sell you our critical materials. But even with this leverage, China still depends heavily on imports from Japan, Europe, and the US for core materials like leading edge silicon wafers, photoresists, and specialty gases. The innovation question. Now, let's talk about the most important question: is China actually innovating, or are they just copying what others have done? If money alone could solve the semiconductor gap, China would have closed it by now. Over 150 billion in government funds have been pledged from 2014 through 2030 to build up their semiconductor sector. But the effectiveness of that spending comes down to research and development and talent. On one hand, the numbers look impressive. In 2021, 2022, 55% of global semiconductor patent applications came from China, double the number from the United States. Chinese universities are producing enormous numbers of engineering graduates, and the country has established dozens of national labs and research institutes focused on semiconductors. The government has even designated 5 key companies: Huawei, SEMIC, YMTC, Nora, and AMEC to receive privileged access to government R&D funding and unlimited financial support to solve bottleneck technologies. Some Chinese companies have tried to recruit foreign talent, offering big salaries to Taiwanese engineers, for example, but this has had limited success and sometimes led to accusations of intellectual property theft. But here's where it gets complicated. Despite all these patents and graduates, there are questions about the quality and efficiency of China's R&D efforts. Chinese semiconductor firms spend an average of 7.6% of their revenue on research and development. That sounds reasonable until you compare it to US firms, which average 18.8%, and it's also below European and Taiwanese companies. Part of this difference is because many Chinese chip companies operate in mature, lower margin segments where R&D spending is traditionally lower. But leading-edge players like Intel, TSMC, and Nvidia routinely spend 15 to 20% of their revenue on R&D to maintain their technological edge. There's also a talent gap in experience. While China produces lots of young engineers, it doesn't yet have as many veteran chip experts with 20-30 years of experience. The kind of deep knowledge that comes from successfully bringing multiple chip generations to market. Software and design. Even if you have the best manufacturing facilities and equipment in the world, you still need sophisticated software to design cutting-edge chips. This brings us to EDA tools, electronic design automation software, and semiconductor intellectual property. For decades, the EDA industry has been dominated by three American companies: Synopsys, Cadence, and Mentor Graphics. Their software is absolutely indispensable for designing complex chips, and this represents a major chokehold on Chinese chip designers. China has recognized this vulnerability and made EDA development a priority. Companies like Empyrean Technology have emerged as leaders, claiming their tools can now fully support 7nm digital design and 5nm analog design. If true, that's genuine progress. The Chinese EDA market share for domestic companies has grown from just 6% in 2018 to about 11.5% by 2020, with projections of 14% by 2025. China even launched a national EDA innovation center in Nanjing in 2023 to coordinate academia and industry efforts. But even Chinese experts admit that domestic tools cannot yet fully replace Synopsys or Cadence for the most complex chips. The best case scenario in the short term is Chinese firms using a mix of domestic and foreign EDA tools while steadily improving their homegrown capabilities. The US understands that EDA is a pressure point and has already barred the sale of EDA tools that support GAA transistor design, technology needed for sub-3nm chips, to China. China's strategy for processor intellectual property is particularly clever. They're going open source. Instead of trying to compete with proprietary architectures like ARM or x86, China is heavily promoting RISC-V, an open source instruction set architecture. RISC-V allows anyone to develop CPU cores without paying royalties, and Chinese companies have embraced it as a pathway to reduce reliance on Western technology. Chinese players are now major contributors to RISC-V development, and Beijing sees it as a chance to build a homegrown processor ecosystem. This is a smart strategy, but it's a long-term play. RISC-V cores still need to prove themselves against ARM cores in terms of performance and software compatibility. The real gap assessment. So, after examining all these factors, how far behind is China really? In manufacturing technology, China is approximately 2 generations behind in logic chips, roughly equivalent to a 5-year gap. While TSMC and Samsung are producing 3nm chips, China's SMIC is working with 7nm technology in limited production. In manufacturing equipment, the gap is even larger. China is essentially frozen out of the most advanced tools and is probably 5 to 10 years behind in developing competitive alternatives. In chip design capabilities, the gap is actually the smallest. Chinese companies have shown they can design very sophisticated chips that are only a couple of years behind the cutting edge. Companies like Huawei's HiSilicon were producing mobile processors that competed directly with Qualcomm's best offerings. The problem is that great chip designs are useless if you can't manufacture them. Many of China's most advanced designs were previously manufactured by TSMC, but sanctions have cut off that option for many Chinese companies. In the design ecosystem, the EDA tools and IP that enable chip development, China remains heavily dependent on foreign technology and is perhaps 5 to 10 years behind the leaders. But here's what makes this situation dynamic rather than static. China isn't standing still. They're investing enormous resources, developing workarounds, and making genuine technological progress. The question isn't whether they'll eventually catch up. It's how long it will take and what the global implications will be. Conclusion. China's semiconductor journey is ultimately a story of ambition meeting reality. Their original goal of 70% self-sufficiency by 2025 was probably unrealistic from the start, but their progress shouldn't be underestimated. They've demonstrated remarkable engineering creativity in working around technology restrictions. They're building massive manufacturing capacity, even if it's focused on mature technologies. They're developing their own equipment and material supply chains, and they're making strategic moves like embracing open source architectures. The semiconductor industry has always been global, with complex supply chains spanning multiple countries and continents. What we're witnessing now is an attempt to create parallel competing ecosystems, one led by the US and its allies, and another developing in China. The implications go far beyond technology. Semiconductors are the foundation of modern economic and military power. Whoever controls advanced chip technology will have enormous influence over the future of artificial intelligence, quantum computing, autonomous vehicles, and countless other technologies that will define the 21st century. China may be behind today, but they're moving fast and investing heavily. The race is far from over, and the outcome will shape our technological future for decades to come. What do you think? Will China eventually achieve semiconductor independence, or will technological and geopolitical barriers prove insurmountable? Let me know your thoughts in the comments below and follow me for more such content.